Hey everybody, Blake here again with another video in my series about spacetime particles where we're trying to use a medium that defines spacetime to kind of simplify some of the physics that we currently rely on, or really just simplifying our physical models. And so in this time we're going to use a galactic slip to remove dark matter. I've also changed the format here a bit. To hopefully make this less painful for everybody and a little bit more organized. Also, I spelled plank wrong last time, and that was shameful. I was spelling it. I think I spelled plank wrong for last 20 years or something. For some reason, I just never add the C in there. But anyway, moving on. So all right, so what we're going to cover in this video will be we'll be talking about space-time in 4 dimensions, and that's maybe not as obvious as it first sounds. Then we're going to look at the galactic rotational curves and how we can solve those without dark matter. And then we'll look at some simulations and analysis. Okay, so general relativity flows in 1 dimension, and that's through time, right? So and it really doesn't move, like information doesn't move from one location to the next. It is transmitted from one location to the next, right? So it's transmitted through waves that travel at sea, or just any sort of, I guess it's not all a wave, but signals are moving at sea. Now, this is similar to, a surface wave on water. So we have a water wave, right? And you see that the wave has velocity, right? But really what's happening is that you can model this with like rotating, little vortices or whatnot. But any particle here or here, that's just kind of moving up and down. Maybe it's moving a little bit left and right, but the particles themselves, the water particles themselves, are not moving at the velocity of the wave. The wave is just moving through the medium at this speed, and that's similar to how we treat gravity or space-time now. We have space-time provides a grid of information, and then we can transmit gravitational waves or any other disturbances at c, so at this wave velocity. All right, so if we have a medium that makes up space-time, we now allow information to flow in 4 dimensions and not just through time. And so now this basically allows for two mechanisms to transfer information. One is at the speed of light. Two is through the flow of the medium. So what that basically means is typically in typical space-time, we have a grid, and that this would information would be changing or whatever we want. It doesn't have to be a sine wave, but some properties of that space-time would be varying at that location. However, if we allow space-time to flow in 4 dimensions, basically what's going to happen is that we can have a blob of STPs. If they move over here, the information is being moved at some velocity that is less than c as well. Now, in the previous video, we talked about de Broglie wavelengths and the double slit experiment, and I said that you can't have a wave that's less than c. And that still holds. These are not, like, what I'm saying here is similar to having sound waves. You can't have a sound wave move less than c. You can have other waves. We can blow the wind, we can move the wind and shuffle the wind. We can create flow in the space-time particles, but we can't create an oscillation or a wave that travels less than c. So it's similar to, imagine if you took a hammer and you hit a piece of aluminum very, very hard, maybe a sledgehammer with a very fine point. you're going to create two waves. One is going to be the distortion of the material, and that's going to travel about the same velocity as the hammer hitting the material. And then you create, a sound wave or a vibration. The first, the wave that's distorting the material isn't going to travel very far, and that's going to lose a lot of its energy quickly. However, the vibration is going to move fast. And you can, so basically, we can create small waves in the space-time particles relative to the momentum of the particle or interaction. But that's not a wave that's going to transmit through the medium like a light signal or something like that. Okay, so how can we use this information to basically replicate the um, observations of the incorrect or the unpredictable rotational curves of galaxies? Well, first we have to have a couple of assumptions, and the first one is orbit drag. Now, general relativity predicts gravitational waves, and these have been confirmed. There's no argument here. And this is a source of energy loss for binary pairs in more complicated systems, right? So if we have a black hole, boy, that's a bigger black hole. They're going to be orbiting around each other. And then this, orbiting is going to create waves in space-time that is going to basically radiate, and eventually these two are going to lose momentum and fall into and collide with each other. Now, let's imagine that we have, two stars orbiting through a medium. Now, you're going to have the same kind of effect, but the gravitational wave energy is proportional to distance and the amount of mass that you're moving, and so it's going to be very small. And this probably might be even a smaller effect. So probably not something that we'll be able to measure, but it might help assisting early galaxies collapse a little faster. But anyway, so if we have two stars and they're orbiting each other, so this here is the inertial sphere, and this is the little bit of space-time that's being dragged along with the body. Now, when you're moving through normal space-time particles, you would expect this to be pretty symmetric. However, if we're orbiting each other, we can perhaps imagine that instead of being these nice perfect spheres, maybe it drags out a little bit here, and maybe these actually continue on, and so there's this nice like long little tail. Maybe it's really sharp, but anyway, and so yeah. So what I'm trying to draw here is that as two stars would be orbiting each other, you could start to create these little tails of your inertial spheres, and these tails can maybe perhaps lose momentum into the medium, and also to help contribute to these falling towards each other. Now, if orbiting bodies lose momentum, it has to lose momentum to something, so it seems reasonable that we can assume that these orbiting bodies would be losing momentum to the space-time particles around it. Now, if the space-time particles are absorbing this momentum, then it's possible, it's not too inconceivable, that perhaps the space-time particles around these orbiting bodies would start to flow with the orbiting bodies. And it's also not too inconceivable if we have enough of these bodies orbiting on the same plane that this effect would grow and become larger and larger, and we could get a more significant swirling pattern. And then finally, we can't have one swirling little galaxy swirl the whole universe. So there has to be some sort of boundary from the swirling momentum to a non-swirling condition. So if you imagine, if this is the center of the galaxy, and things are moving, at some point very far away, this is velocity. I don't know, velocity of the galaxy. Well, then, actually, maybe this would be space-time particles. And this also, so for some distance far away from the center of the galaxy, it needs to have, a zero contribution here. Okay, so the ultimate takeaways here is that a loss of space-time particles from the tail would decrease the inertial sphere of the orbiting body and contribute to faster orbital decays. Momentum, this loss of STPs acts as a momentum transfer from the body to the medium. And, the big takeaway here is that this new effect would operate on the order of the momentum / velocity of the bodies. So there's kind of a relationship. You have a bigger body moving faster, it's going to have, a comparable effect to the medium. Now, the next assumption is that light is fast and gravity is relative to the medium. Is that two assumptions? Maybe yeah. Anyway, assumption 2, which may be 2 and 3, but whatever. So light is much faster than the orbits of the stars and the galaxies that we're looking at. If we're thinking about, most galaxies, you could say 200 kilometers per second is a good kind of average velocity for bodies in motion around the galaxy. And this is only 0.067% of the speed of light. So essentially, to a little photon, all these bodies are stationary, right? So like if you were running a 100-meter dash, this is a person running, I guess maybe. Anyway, if you're running and you have you're competing against somebody that's going 0.06% of your speed, and you give them a 90-meter head start, they're still only going to cover 67 millimeters by the time you finish. So they're essentially going to see you as not moving. What I'm trying to say here is if the bodies are essentially standing still relative to the medium, we can make an argument that maybe the gravitational forces and the accelerations are all relative to a moving medium. And so like a body must have the necessary velocity relative to the medium to overcome gravity. So if a body has zero velocity relative to the field, so the rotating medium, we could still, if the medium is moving, we would still see it as having velocity relative to an observer. Similar thing here is if you had an airplane. Is this airplane needs 30 meters per second to fly. However, if you get a tailwind of typically the tailwind would push the plane along, but if it doesn't, the plane's going to be moving only 20 meters per second relative to the tailwind, and it is going to ultimately, you know, your airspeed is going to be 20, and so this poor plane is going to come down. So now we're just going to use kind of this general idea as a way to start simulating some galaxies here. And we're going to start with a 2D simulation. Okay, so I'm going to run this simulation. And essentially what we're going to be simulating is we have the black, which is just what we observe. And by that, I would just mean that we're going to assume that there's a constant velocity regardless of radius. So they're all moving at 200 kilometers per second. The white, however, are simulated values, and they're just going to be they're just due to Newton's laws of gravity. So as you move farther away, there's less force due to gravity, and so you need less centripetal acceleration to keep them from falling in. So they're going to move slower as you get further away from the center of the bulge. Now they're also, however, going to be affected by the medium. So if the medium starts moving, the white stars will also move a little bit faster as well. And I'm going to essentially allow momentum from the bulge to be transferred into the medium kind of at a constant rate. And I'm going to say that the edge here needs to have zero velocity. So let's look what this looks like. And here's the scale on the left. Blue is 0 for the medium. You can see white's moving pretty slow and black is faster. Now we're going to pause it. So essentially here is I've allowed momentum to bleed into the medium. So you could just maybe assume that the bulge is spinning at some value. And this is a rough simulation, so it doesn't matter too much. But and so as momentum gets bleed in the medium, you start to get about that 100 kilometers per second right around the bulge, and it starts to fall off. And so if I continue to let this transfer momentum, what happens? You can see it's still growing, but because there's zero velocity at the edge, we're going to get this gradient, because as you spread out, you got more drag, maybe not drag, but a less efficient momentum transfer. And so you can see we get this kind of this gradient. And try to watch at the, if you look at the planets or the stars, let's bring this back. White is actually moving a little faster than the black stars at this point, and that's not good. But again, out here, black's moving way faster than white, and so that is also not good. So basically, this is a failed simulation. Now, if we look at the velocity profiles, these were the black ones. So I basically just said all of my black stars are going to move at 200 kilometers per second. This is not a perfect representation of what we see, but roughly it's close enough for what we're doing. And then you can see here is the calculated values for our first rough estimate. They fall off as you get further away. And this is before we start the simulation. And so once we run the simulation, momentum gets transferred into the medium, and now the observed velocities of the white stars are way faster. So this is all bad. And however, they're very bad over here. So we got bad and bad. Nothing's really right except for just this one spot. So ultimately, the velocity gradient isn't even close to the correct answer. And we can't transfer enough momentum from the center of the bulge into the medium to rotate the edges. So let's add slip. I've said this before, that one of the things that physicists don't like are discontinuities. And unfortunately, they're also one of the perfect solutions to a lot of the problems that we are trying to solve right now. So we're going to do the same simulation again, same thing, black and white, but at the edges, we're going to create a slip condition where we do not transfer momentum past this boundary. Okay, so what does this look like? So same kind of thing. We are transferring momentum from the center to the edges, but now look, we continue to transfer momentum throughout this entire area, all the way up to this slip, this kind of discontinuity at the edges. And I can kind of speed this up so we don't have to sit here all day. And so now if I pause it, you can see the medium, basically we spun it at 100 kilometers per second at the center, and that transferred all the way to the edges. If we look at the stars out here, you can see we get this nice, I guess this black one and this seems like they're almost going the same speed. Maybe not perfectly, but they're going kind of nicely. But at the center, we still got this, we have a problem with the whites going quite a bit faster than the black. So this is something. Let's look at the plots and we'll continue to talk about them. So you can see here, we've moved the velocity of the simulated stars way too high. But the end here is actually an okay agreement. This little drop here is just because we're dropping off over that boundary. Okay, so let's review. So we have three main problems with this. Again, we do not get the correct velocity profiles. And there's kind of two problems. One is if we were to transfer momentum in this way, you would expect there to be this weird feedback where the center would spin up faster and faster and faster, and the edges would spin up faster and faster, faster, and the whole thing would spin up until some unreasonable velocity. And then the third problem is this is only a two-dimensional solution. Fortunately, if we look at this in 3 dimensions, which is significantly more difficult, we can solve all of our problems. So here, now we're going to start a 3D analysis. It's not quite the same simulation, but we'll go with that. So before I mentioned something briefly called the mass vector. And this is not really gravity, but it's just a property of space-time that's relative to the masses or something in the vicinity. So we don't really know what this is yet. We haven't talked about it much. We'll go more into detail about it. But for now, we're just going to use the gravitational field. And we're going to simulate this whole thing using density distributions from established sources. So we're going to try to make this as realistic as possible. And we're going to use the dark matter models because these dark matter models are all trying to solve the same problem, is that there's a discrepancy in velocity for observed and what the baryonic matter can, the baryonic mass contribution component. And so essentially the baryonic mass will say you need to have an orbit of 10 meters per second or kilometers per second. And then however we observe it at 100, then you would want to have a mass of dark matter to somehow make up that 90 kilometer per second difference. And so we're just going to use that 90 kilometer per second difference as our way to solve this or look at these situations. Now, when I'm talking about the mass vector, whatever, this is a color. So essentially we're going to have some sort of relationship, and I draw the mass vector like this. And for this case, we're going to say it is proportional to the gravitational field, and we're going to look at the slip velocity. And I'm going to say that when the mass vector or the gravitational field is small, we're going to have a high velocity or a high allowable slip. However, when your gravitational field or mass vector gets bigger, basically space-time gets a little bit less compliant, or space-time doesn't allow for as much slipping. It gets more tight or something. I don't know how you want to describe it. Basically, you get a less allowable slip velocity from one place to the next. And of course, this would be at, center of some mass. And so our simulations, we're going to basically have, simulations are going to have a center bulge. And I'm surprised I can spell bulge right, because that D always kills me. Then you're going to have kind of different models here, but essentially you're going to have and I don't know if it should be C disk with a C or disk with a K. Somebody smarter than me knows the answer, but thin disk. And so essentially when we're looking at these galaxies, such as the Milky Way, you're going to have, an area of mass in the center that's more spherically distributed. So, and that's going to be the bulge density distribution. Then you're going to have an area where the disk is quite thick. And so then you're going to also have a thin disk. And so we're going to use kind of something like this, but we need to remember that this. So what this means, I'll do green. So we can use this curve on areas outside of the distribution of mass, right? So we're going to be looking at basically the edges of the galaxy. This curve does not apply inside of in between the masses of the galaxy. So it's not going to apply inside the bulge. It's not going to apply inside the disks or anything like that. So we'll look at that more down the road, but we just remember that we're mostly interested outside of the galaxy. And that's where this curve is going to be more accurate. All right, this is the data that we're using to simulate the mass distribution in the Milky Way. I'm using the sources from this paper. I'm not sure. They might have gotten these actual values from other sources, but this paper did a really good job explaining and detailing their methods here. So you can see we have all of these different sources of mass. The bulge is going to be kind of more spherical and centered around the center. And then these other components are all going to be double exponential profiles. So basically disks with some sort of thickness parameter that falls off as you get further away from the center, and so the scale length kind of decides how fast it falls off as you move away. And then the same thing about the height. This is basically kind of describing the thickness. And so over here we have a plot of basically the orbital velocity that each of these components requires to create a stable orbit. So if we only had the bulge is right here, and that's this line. If there's only the bulge in the Milky Way and we were at 10 kiloparsecs from the center, we would need to have, boy, I picked some, boy, what would that be? 75 kilometers per second orbital speed necessary to counteract that gravitational potential. And so then you can see that we have, the other components as well, and they have different profiles because their density profiles are different. Um, and so in order to look at this, you can kind of sum up. You don't really actually sum up, it's a root sum. So summing in quadrature. Um, but when you do that, you can kind of get the contribution to all the baryonic mass, and that would be this line. And so this is where we get this huge discrepancy. This is how fast bodies should be orbiting at these different radii. However, when you look at the data and you make measurements, these little dots with error bars are what we're seeing. And there's a clear problem here. And so essentially what this paper, or what has been done in the past, is you get this dark matter model, and that will basically, when you add the dark matter into the mix, you can create this red curve, which now fits the data very nicely. And so essentially what I did is I said, well, the baryonic mass is what we have for our gravitational influence, and then this delta in velocity is going to be due to the swirling of the galaxy. Um, and so we're really going to be trying to make up the difference here um, with the flow of space-time particles. Now, I am not from this field initially, and so making all of this data here turn into nice plots is not actually as simple as one would hope. And so my first step was just to recreate this plot using the data on this side. And so that's what the next slide is. So you can see, this is roughly 220, 30 kilometers per second. I have a weird angle. So, and the data is actually really easy to confirm because it's just a simple input. So looking at that, we'll go to the next slide, and this is essentially my recreation of that slide using just the parameters in that table. And you can see here are those measurements, and they fit nicely with the black line that I've created, the black time. The black line is my target velocity. The baryonic matter is this line here. So we're all, so basically with this, it was just a confirmation that I didn't have some massive error in my analysis. Because from here, we have to basically create the potential field and then do the derivative of that to get the gravitational field for the entire galaxy. So this is the result of that difference between the baryonic mass contribution and our observation. And so we have kind of a low, very little required swirling of the galaxy needed at the center, and then it increases to about a maximum close to 100 kilometers per second, and then it gradually falls off. This is only for the Milky Way. This swirling, or this required flow, could vary from galaxy to galaxy. It just kind of depends on the mass distribution of the galaxy, and perhaps maybe how long it has been undisturbed by other galaxies and whatnot. So All right, so let's look at the cross section of the galaxy. We're going to say the center is somewhere over here, and it's going to be, the z component is pointing upward, and so x and y is going to be, um, in this page, basically the galaxy is going to be rotating such that its matter is rotating in the x and y plane. Z is pointing up. You can then say that velocity is going to be going into the page on this side, out of the page on this side. And we're really only worried in one quadrant because we're going to have symmetry over the z-axis, and it's cylindrically symmetric around the z-axis, at least for this model, and then it's going to be symmetric over the x and y plane. So we're only looking in one axis. And we know very far away, somewhere, we have the velocity of the medium is going to be 0. And so basically the galaxy cannot swirl the medium very far away. So that's what this is. And we also know above we have the velocity of the medium is going to be 0, or, velocity of the STPs, whatever we want to call it here. And we know this because the galaxy can't, if it can't swirl indefinitely far away from the radius in the plane that it's swirling, it certainly can't swirl infinitely far away above the galaxy as well. And so what I'm going to assume is that we're interested in kind of this boundary between a rotating medium and a non-rotating medium. And so this is going to be like the slip boundary of the slip condition. As a rough estimate, I'm going to say that the slip boundary starts at the center of the galaxy. It's going to come up to some point out here, and then it's going to come sharply down, right? So, and the reason why I'm saying that there's an angle is because momentum transfer is being transferred in the radial direction as all of the mass is working together to kind of lose momentum, or transfer momentum into the medium. So as momentum is transferred in the medium, we're going to rotate faster and faster until we reach the slip condition. Once we reach the slip condition, no more momentum is going to be transferred past this boundary because now we're slipping. And if we don't transfer any momentum over that boundary, that means that we start to get this feedback where it's easier. We can get a larger amount of momentum transfer, or we can get faster and faster orbital speeds at the boundary, and the whole thing would run away. However, there's nothing to say that some of this momentum is going to be kind of bled off in the z direction as well. Now, why is that important? So there's going to be this angle theta here. And so as theta gets larger, we have a less and less efficient momentum transfer in that z direction. And that's simply just because all of the momentum that we're interested in is in the xy plane, and so it is working together to move purely in the radial. But some of the momentum is getting dragged along in the z as well, or some of the medium is getting dragged along. And so basically what happens is we spin up a narrow band of the galaxy to the slip condition on the outside, and maybe this slip condition grows as the galaxy is establishing itself. This slip condition can kind of grow outward, and as it's growing outward, some of the momentum is working its way in the z direction, and then we're going to reach kind of a stable part where it is now not able to transfer enough momentum in the z direction to make this angle steeper. And so it's going to be kind of this nice, it's going to be a stabilizing feedback loop. We're going to have momentum transfer radially. That's going to make everything move faster, but then it's going to try to move more in the z direction or drag more medium around in the z direction. However, that's just going to be, instead it's going to be bled off, and it's just going to be a pure momentum loss. You know, this is going to be probably just a small amount, but enough to stabilize the shape of the galaxy and to keep it from running away indefinitely. Um, and so, in order to inform, this decision, these decisions a little bit better, we can look at a couple other images and some other data. One of which is the Fermi bubbles. The Fermi bubbles are just a source of gamma and X-ray emissions that we noticed around the galaxy center. And I'm going to argue that, this nice symmetric distribution of energy would likely be corrupted if the center was swirling. So I would like to argue that perhaps the slip condition is going to start somewhere along this boundary edge. And so we're going to use that to inform our decision for our initial guess. Okay, so this paper was looking at the disk flaring and they could do some Milky Way simulations and whatnot. They were specifically looking at the age of stars, grouping the stars by age, and I believe that's what these different colors represent. But I'm just using it as another way to make an informed guess. And so I'd like to make a guess that maybe around 4 kiloparsecs, at around 20 kiloparsecs, we're going to have some sort of reference point for our slip condition. And basically, yeah, it's nothing too scientific here. It's just an informed guess, and let's see where that takes us. Okay, so we've got this simulation. I'm going to explain this. So basically, here is the center of the galaxy. We have R in this direction. Here is where we are, our solar system. Z is in this direction, so it's the same thing. So we're rotating basically. If you imagine a dinner plate, we've broken the dinner plate in half, and now we're looking at that edge. And so we have basically, I've modeled this with all the different potentials. So we have the bulge potential, disk potential, warm potential, H1 potential, dihydrogen. I don't even know if that's what it's called, H2, but hydrogen. Then we have the cold, which is just cold dust. And then this is the potential of everything added together. Then we can use that, the derivative of the potential, to get the gravitational field. And it is not very exciting. But we are basically now guessing at what this slip condition would look like. So we're out here, we're about 20 kiloparsecs. Here is, this was influenced by the Fermi bubbles. And then we're just kind of coming out here to 4 or 5 kiloparsecs from those other plots. Those other plots were scale heights for the Z, and that just means that at that location we're starting to fall off dramatically. So, the actual matter extends past those scale heights. It's not like a sharp cutoff. So Um, Now, I'm going to use this line to collect data, and we're going to look at that data versus the the velocities, the rotational velocity error that we measure. So this is the velocity that everybody is associating to dark matter, and I'm going to just say that that velocity is due to the rotation of the galaxies. All right, so I've collected the data along that line that I made, and we have made this plot, and we have the gravitational field on this axis, and we're just grabbing the data from each one of those locations, and we're plotting it against the velocity we need. Um, okay, so we've taken the data along that line, or each one of those locations, and I've essentially plotted the gravitational field at one of those locations against the required flow velocity of the galaxy to make the data, our observations match. And so then we get this kind of nice, this smooth trend. And, but this is kind of an artificial trend because we just grabbed some random line and shape. And so in a perfect world, we would have, you know, the exact equation here, but we don't, and we're still looking for that. So we're just going to kind of guess right now that the slip velocity over here is is an exponential fit. So now we have this kind of artificial fit or approximation to the slip velocity that's dependent on the gravitational field. And we can look at all of the data and just see where this equation, this v slip, actually equals the flow velocity of the galaxy from measurements. And so we're going to look at that. So essentially plotting I guess we'll call it delta v equals v slip minus, so v not even measured, we'll just call it v flow. And so, and this is all positive, right? So when we're looking at the cross between, so anything that's positive is gray, and anything that's zero or equal or zero or less is colored. And so this boundary between gray and colored is essentially where v slip equals the velocity of the medium. And so you can see we actually get this really interesting shape. And so basically what I'm arguing here is that this is the shape of the, the slipping galactic medium. But our biggest problem here is that I am plotting against some random, this gray curve is a random curve that I guessed, and I'm fitting against some random function. So just to look a little bit more, let's look at some other functions. So this is just the, if we were to fit the data perfectly, I'm not even going to show you what those values stand for because, or what the coefficients are because it doesn't make any sense. But you can see that if we match it perfectly, we get a much better agreement with this line that I made up. So here's my attempt to come up with a smarter fit that's not just pulling equations out of the trash bin. But here is an equation that basically when x is 0, the velocity, your slip velocity, is going to equal the speed of light. And then, follow the data a little bit better as the G field gets stronger. And then here are the coefficients that I used to build this curve. And so what does this look like? Same thing as above. We get kind of a similar thing. It's almost like a giant dumbbell. And again, this is the cross section, would be the cross section of a plate if you broke it in half. But again, this is like, the big thing that we need to do here is come up with the equation for the slip velocity relative to the gravitational field. And this is just kind of showing potential. I'm not claiming that this is right at all, but it's just something I started using. Now we're going to look at some tests to kind of validate this idea. So there's going to be a similar effect with gravitational lensing, but there's also going to be a contribution due to the flow. And so what would be interesting is to look at how light bends around, and maybe it's actually, but we would look at how we get like a delta due to the rotation. So we should expect we might get these big old globules, I don't know, of space-time that are moving. And I guess if you get light, it's going to want to bend here, and maybe it's going to do something. So we would basically have to use a different model. We get a lot of these, like JWS just did some dark matter maps. And now if we, instead of looking at the distortions due to gravitational effects, we could look at the distortions due to different flowing of space-time. This would be something interesting. We could also look at galaxy mergers with this in mind. And so, boy, I guess maybe I should do a down arrow. If we're following the right hand. So imagine if we had two galaxies merging in this direction. These two, the space-time flow might, this might start to get into some weird kind of thing that might help the merging, that might inhibit, it might eject space-time, as they're merging. And so then we would get some sort of gravitational or light distortion behind this part. Now, if galaxies are both going in the same direction, you might get some sort of compression here, so closer time. That might contribute to more heating, maybe more ejection. Maybe there'd be a more energy loss. It'd help to explain why galaxies can merge so quickly and match. But we'll have to look at this a little bit more later, because it's interesting when these both merge very closely, then you're going to have maybe all of your matter sharing the same slip, but you still have momentum as these are brought apart, and then this lines are going to eventually have to snap. And they're going to have to go back to being separate again. So anyway, so there's a lot to look at with galaxy mergers. We also got, this is an idea from Heretical Physics by Van der Voos. And his idea was kind of similar. If the galaxy is rotating, then light is actually going to be slowed um, from one side to the next. So if we have a supernova in the distance, the amount of time it takes for the light from the supernova to go pass from over one side of the galaxy to the next is going to be different. And so, especially with some of the new telescopes that are imaging the sky and looking for these supernovas, if you would measure supernova and another one in the same spot years later, this would be a good um, confirmation of this idea. My only problem with this is that I'm arguing that the velocity profile of the galaxy is not constant, and so if you're going through the center of the galaxy with some deflection, there's probably not going to be a long delay difference between the two sides. You'd really want to somehow get it to go through, the largest, these outside light vectors are going to have than these smaller ones. But anyway, that's just something else we could look for. And so kind of the next steps for this is we're going to look at the distortions due to the space-time flow, which I kind of showed in some of the galaxy mergers. I'd also come back to the particle wiggles, which corresponds to the double slit experiment. And the particle wiggles is really trying to help us come up with a slip velocity equation. If we can fundamentally understand what allows for this slip condition to occur, we should be able to come up with a more insightful equation. And then fun stuff of just like whatever might, I'd like to explain away some of the other like dark energy or the inflaton field and stuff like that way. So anyway, thank you for listening and watching. And if you have any questions, please let me know. I will see you next time.